in case we would like to make some judgments about whether or not some data is normally distributed, it makes sense to first look at a normal distribution. As I said before, a normal distribution is characterized completely in terms of the mean and the standard deviation. That's the mean. And the standard deviation would be given here, roughly. Mathematically speaking, the standard deviation gives us the distance between the function and the mean at the so-called inflection point. Now, in any case, a normal distribution is a symmetrical distribution. That's one important feature, and the second is it has this special bell shape here. If we take a look at the histogram from the data, it's kind of obvious that this does not really look normal, and that's for two reasons. If I would now use this sketch here, if I would superimpose a normal distribution here, where approximately the mean would be where we know it to be, we see two main deviations from a normal shape. First, the empirical distribution is skewed, and second, it is in a way more peaked than the bell shape of a normal distribution. Now, this is visual judgment. We would rather look at some statistics in that summary table here, and the two statistics which support our visual judgment is the skew, which has no units of measurement, which makes it kind of difficult to interpret, but the skew would be 0 for a normal distribution, and if the distribution looks like this one, where the left tail is rather steep and the right tail is rather flat, then the skewness is positive. If it was the opposite, that the left tail would be flat and the right tail would be steep, the skewness would be negative. And the more skewed, the larger that number would be in absolute terms. So skewness is a measure that allows us to make judgments about the symmetry of a distribution. The other measure here in this table is kurtosis. The kurtosis of a normal distribution is 0, again has no units of measurement, and it says something about the shape of the distribution. A bell shape, like in the normal case, would result in a kurtosis of 0. If it's above 0, then, as I said before, the peak of the empirical distribution would be somehow more pronounced, and I exaggerate here a little, than the normal bell curve. One could also view this kurtosis as a measure to what extent a distribution is squeezed from left and right. The kurtosis would be negative if the opposite was true, namely if a distribution would not be squeezed or peaked at all, but rather flat. So that's the two measures from the summary statistic table, which allows us to make these judgments. Finally, I would like to take a look at the rules of thumb that we've looked at before. These probabilities here are based on assuming a normal distribution. Now, if we are now comparing these probabilities to the frequencies, percentage frequencies that we find in the data, we can also support our judgments regarding the normality of a distribution. And for that purpose, I use the frequency function again, refer to the data of the prices, and to the boundaries that we've computed before, so it would be minus 3 standard deviations from the mean. And for completeness, I divide that immediately by the total number of cases to get a percentage. Now if I compute all those percentages, for instance this one, gives us a 10 or 11% probability or chance of values in that data set that are below 100,004, which was the mean minus 1 standard deviation. And a comparison of these probabilities with the normal probabilities, so let's call these normal and these empirical again, but this time we are comparing on the basis of the boundaries that are given by the 3 rules of thumb. We see that the probability empirically to find values below the mean is much higher than the 50% based on a normal distribution. So we have almost 60% below the mean. And this coincides with the fact that the mean is above the median. And a simple explanation for that fact could be based on noting that the right tail is very flat, reaches out rather far, so there's a few rather large prices in here which make the mean become larger and larger the more extreme they would be. And finally, these 3 values, 2/3, 95%, and about everything, based on the normal distribution and the 3 boundaries, we could compute them based on our empirical frequencies, empirical distribution, and we see that within that 1 standard deviation range around the mean, we don't find the 2/3 approximately that we would expect in a normal case. We find almost a quarter. So that's a clear indication that this data is not normal. It looks a bit better if we compare the 95 here. So for the 2 standard deviation range, we're about at the 94% empirically. And again, if we compare the 3 standard deviation rule of thumb, we see actually there was hardly anything to be expected outside these 2 boundaries from a normal perspective. So that would be just a very small number of less than 1%, far less than 1% outside that range, whereas we find almost 2.5% outside the 3 standard deviation range. So making judgments about whether some data points are extreme on the basis of a normal distribution would look differently from another distribution's point of view.